Guys, so this is your helpful hint video for your multiple choice for this week. Let's go ahead and take a look at an example to help you guys out with number one. For each problem, find the values of C that satisfy the mean value theorem. Now, you don't need to go through and make sure you can do the mean value theorem on this. You just need to apply it. But just for the heck of it, I will review it really quick. This is a continuous and differentiable function on any interval because it's a polynomial. So yes, the mean value theorem applies. And what does the mean value theorem state? The mean value theorem states that there is some value C for which the derivative at that point is equal to the average rate of change on the interval that we are concerned with. Okay, so what we need to do then is we want to find this value of C, all right? So the first thing I'm going to do is I'm going to take the derivative of this function and plug C into it. So if you took the derivative of it, you're going to get 3x squared minus 8x, and that's that. So plugging C into that, we get 3c squared minus 8. Now for this half over here, we need to actually plug 3 into the original function and 0 so we can get the numerator figured out. So let's find out what f of 3 is. So if I were to plug 3 in for x cubed, I'm going to get 27. And then if I were to plug 3 in here, I'm going to get 36. So 27 take away 36 is negative 9 plus 7 is negative 2. So f of 3 is negative 2. If you plug in 0, these just go away and you're left with 7. So we have 7 there. And on the bottom we have 3. Now, continuing this expression up here to the top, we have 3c squared minus 8c equals negative 9 over 3 is negative 3. Now this is a quadratic expression. So if you want to solve this, you need to move everything over to one side. And if possible, factor it, but I'm pretty sure that this doesn't factor this time. So when a quadratic doesn't factor, the way that you solve it is you solve it by doing the quadratic formula. Okay, I'll go ahead and do my quadratic formula on it, and that will tell us what the value of C is. Okay. Erase all my stuff here. I need some writing space. All right. So the quadratic formula is or in this case C equals negative b plus or minus the square root of b squared minus 4 times a times that last number all over 2a. And we're going to plug in our numbers. This is the b value, so I'm going to put negative 8 here and here. This is the a value, so that goes here and here. And that value goes in last here. And now we just get to simplify some stuff, so that makes 8, 64, 36, 6. All right, 64 take away 36. 28. So this square root here becomes the square root of 28, and we could break that down into 7 times 4 and 2 times 2. So the way you simplify a square root is after you break it down, you take out the pairs that match as 1. So this whole thing here simplifies to 2 square root of 7. So now we have 8 plus or minus 2 square root 7 over 6. The last thing you'll do is you're going to, if possible, reduce all three of these numbers at once. You can only do it if all three of them have something in common. Like if you didn't have a number here, for instance, you wouldn't be able to reduce. but in this case we do. All three of these can be reduced by 2. And so these are your two possible values of c. However, one of them is one we're not going to use because, remember, we're looking for a value of c that's on this interval. And the one where you would subtract, well, let's see what those things are really quick. We have 4 plus the square root of 7 over 3, and then we have 4 minus the square root of 7 over 3. Now, if you were to add the square root of 7, now, the square root of 7 is going to be a little bit more than 2. So if you add 4 to that, you get 6, and if you divide that by 3, you're going to get something approximately like 2-ish. Whereas with this one, if you do 4 take away 2, something a little bit more than 2, you're going to end up with like 2 or something slightly less than 2. So 2 divided by 3, this could also work also. There might actually be 2 solutions for this one. To be sure, I'm going to guess it's about 0.6. But to be sure, I'm going to check my answers here. I mean, it's so long as it doesn't come out to be negative, and I don't think it will. So I think both of these are solutions. But just so you know, your answer has to be on the interval from 0 to 3. Yeah, they included both. So, but just be aware, sometimes you'll get 2 answers and one of them is not on the interval, so you'll discard that particular answer. Move on to the next one. So I'm going to do a couple of examples for you guys for numbers 2 through 4. For these problems, what we're going to try to do is we're going to try to see, does the mean value theorem apply? And if it can't, we want to explain why it does. Okay, so first of all, let's review what the mean value theorem is. I did it on the last problem a little bit, but now I'm going to give you more of a picture idea. If you've already done the FRQ, then this will probably just be an extra review for you. But basically, the mean value theorem states that if you have a function that goes from one point to another and it's continuous and differentiable on that interval, then the average rate of change, which is represented by a secant line that goes through the endpoints, has an equivalent instantaneous rate of change somewhere along that curve. So I would say, like, for instance, like right about here, the instantaneous rate of change is parallel, or the tangent line is parallel to the secant line, which means the instantaneous rate of change is equal to the average rate of change. And there's at least one, but that's what the mean value theorem guarantees, is there's at least one. But in this case, there's actually 2 based on the picture that I've drawn here. So you could have more than. So that's what the mean value theorem states, and that's where we get that whole setup here, because the slope of the tangent line is f prime, and the slope of this black line is the f minus f over b minus a that I showed you in the last problem. And so since those slopes are equal, you set them equal and solve, right? So that's the mean value theorem. However, what criteria are necessary for this to apply? Well, you can't have any holes, gaps, or jumps in your function, because if you did, then what happens if the hole was here at that one point where that slope would have existed? Well, then you wouldn't have an answer anymore, right? So it needs to be continuous, and where not only that, it has to be continuous at the endpoints. If the endpoints aren't included, then you can't even get your average rate anyway, because you have to plug your endpoints in. So it has to be continuous on the closed interval. So there can't be any holes, gaps, or jumps anywhere. Now, it also needs to be differentiable though, right? Because we're trying to find a place where the derivative equals the average rate. And if the derivative doesn't exist, then, well, then obviously you just lost your answer, right? So the derivative has to exist on this whole interval, but we don't include the endpoints. We don't include the endpoints in this one. So it just needs to be differentiable on the open interval. Okay, so those are the requirements for the MVT to actually apply. Now let me clean this up a little bit. Okay, so let's go ahead and we'll do an example here. So here is this function, the square root of x squared minus 9. So First of all, this is the function f. We'll just call that f. Now, where is f continuous at? Well, f is continuous anywhere where it exists. So what's underneath of the square root here has to be greater than 0. So x squared minus 9 has to be greater than 0. Well, it can also be equal to 0, right? You can have whatever's in here can be 0 or positive, but it can't be negative because as soon as you get a negative under your square root, it's an undefined answer, right? So for continuity, this function is continuous so long as x squared minus 9 is greater than or equal to 0. So we're going to go ahead and solve for x squared here to figure out what x is allowed to be. Now we're going to take the square root of this on both sides, but when you do that, you get two answers, a positive 3 and a negative 3. But for the negative 3, you will reverse the inequality around. Okay? Anytime you're dealing with inequalities, if you do something that causes the other side to change signs by square rooting or multiplying, for instance, you're going to reverse the inequality. Okay? So x can be one of two things. X can either be less than or equal to a negative 3, or it can be greater than or equal to a positive 3. So for our function, it's got to be, for its continuity, this, we need, that's where it's continuous. So this function is continuous anytime x is less than or equal to negative 3, or greater than or equal to a positive 3. Now what about where is it differentiable? Well, to do that, we need to find the derivative. Okay, now, how do you take the derivative of the square root? Well, you do 1 over 2 times the square root we have. And then you also multiply it by the derivative of the inside, which is 2x. And in this case, the 2 on the top and bottom just cancel each other out. So there's our derivative. Now, this derivative pretty much has the same answer as the continuity, right? So long as this actually has an answer to it, which is for anything that's less than or equal to 3 or greater than or equal to 3, we're good. However, there is a difference. Remember how we said that this can equal 0? Because the square root of 0 exists, right? But when you take the derivative, you get, if you have 0 on the bottom, that's undefined. So differentiably speaking, it's the same thing as continuity here, but the only difference is it can't be equal to 3. Okay, so in terms of continuity, my function can be less than or equal to 3, or greater than or equal to 3. But in terms of differentiability, it has to be only less than 3 and greater than 3. Okay, so keeping that in mind, let's go ahead and do some problems here. So the question we're being asked here in the directions is, can you apply the MVT to this problem? Well, that kind of depends, right? It depends on the interval. So let's say I gave you guys an interval that looks like this. Can the MVT apply to this function on that interval? Well, remember, it has to be continuous on the closed interval. So, is this function continuous on the interval 4 to 5? Well, remember, the function is continuous for anything that is either less than or equal to negative 3 or greater than or equal to 3. Well, both of these points are greater than or equal to 3. So since they're greater than 3, my function is continuous on the interval. Now, is it differentiable on that interval? Well, once again, they're both greater than 3, so we're good. So for this one, the answer would be yes, because the interval we're looking at is a place where this function is both continuous and differentiable. All right? But let's make a change here now. Let's say I gave you this interval. is it continuous on that interval? The answer is no. It's not continuous on the interval. Here's why. This function is only continuous for numbers that are less than or equal to -3 or numbers greater than or equal to -3. So I'll draw you a number line to help you see that. Here's -3, here's +3. So my function exists from here and over, But if my interval is going from -4 to +4, there's a gap in the middle here where the function doesn't even exist. The function's not continuous on that interval there. So we would say that this function is not continuous on the interval, and therefore your answer to this would be no, since the function is not continuous on that interval. Okay? Let's do another one. What if I made a slight change here? Let's say I had this now. Well, that's actually kind of the same thing. Let me erase that. That's not going to change my answer at all. Let me give a different answer. What if I had this? 3 to 5. Okay, now here's where things get kind of strange and interesting, so pay close attention. So, is it continuous on this interval? The answer is yes, because x can equal 3. That's what the bracket means. It can equal 3. And it can also equal 5 because both of those numbers are greater than or equal to 5. So we're going from 3 to 5 and there's no holes, gaps, or jumps on that interval. The function is continuous on that entire interval. Is it differentiable on that interval? At first, you might be tempted to say no. And the reason why you might be tempted to say no is because remember how we said that if it's differentiable, it can't equal 3. But uh-oh, it equals 3 here. We're using a bracket. Well, here's the thing, though. It doesn't have to be differentiable on the closed interval. It needs to be differentiable only on the open interval. So if I change this to become this, now it is differentiable. So this is continuous on that interval, and it is differentiable on this interval, starting at 3 and anything greater. Okay, so that one is actually a yes. It's continuous on the closed interval and differentiable on the open interval. So in summary, what do we have to do then? Well, you have to know where your function is continuous and where it's discontinuous. And then you have to remember that it needs to be continuous on a closed interval and differentiable on an open interval. All right, so that's for numbers 2 through 4. For numbers 5 through 6, a similar question. We're asking you, can the extreme value theorem be applied? Well, the extreme value theorem is a different theorem, so let's talk about what that is first. The extreme value theorem basically says that if you have a continuous function from one endpoint to another on a closed interval, then there has to be an absolute max and an absolute min somewhere on that interval. Here's another example, absolute min and absolute max. The absolute min and max occur either at critical values where the relative extrema are located, or they happen at the endpoints. But if your function has any holes, gaps, or jumps on them, then you don't really know for sure if there's a max anymore. So here, that would have been my max, but since it's an open dot, we don't have a max anymore. This would have been my min, but since there's an open dot, we don't have a minimum anymore. So the function has to be continuous on the closed interval. So the only requirement for there to be a guarantee that there is an extreme value theorem, or extreme value, is that it has to be continuous on the closed interval, endpoints included. Okay? So what is the extreme value for this function? Is it continuous on this interval? So now I know that you guys are probably a little out of practice with secant and what it is, so you may not know where secant is continuous or not. Now I'm going to show you guys two ways to do this. One way is to use a handout which I gave to you guys a little while back, and I'll also include it in this week's lesson for you. Where is it? Here we go. All right, so this is what I call the continuity of common functions worksheet. It tells you where they're continuous and where they're discontinuous. So if we were to scroll down here to secant, you guys can see that secant looks like this. And these dotted lines are vertical asymptotes. And those are places where secant is not continuous. So secant's intervals of continuity are kind of like an infinite connection of various intervals where it's continuous. And where it's discontinuous is anywhere where the argument, the part that's inside the parentheses, is equal to pi over 2 plus n pi. Now, an easy way of saying that is that secant is going to be discontinuous at pi over 2 plus any pi value added onto that. So thinking of your unit circle, if you go from pi over 2 and you add pi to that, which is half a circle, you're down at the bottom, which is 3 pi over 2. So thinking of that then in terms of a unit circle, right? We know pi over 2 is up here. If you add pi to that, that puts you down here. So basically, anytime you're on the y-axis, you end up with a discontinuity for secant. Okay, now look at our interval though. We're going from pi over 6 to pi over 3. So that's here to here. So I'm going from this spot to this spot on my unit circle. My discontinuities are here. So obviously, there's no discontinuities on that interval. And so we're good to go. Okay, so this one we would say yes, there is an extreme value. So yes, EBT applies since secant is continuous on that interval. Okay, let's take a look at another problem here. Here's another one. So let's bring back that picture again. So bearing in mind we have some discontinuities here at pi over 2 and at 3 pi over 2, and any multiple of pi over 2 after that as well. So in this case, our interval is different. We're going from 2 pi over 3, which is over here, to 5 pi over 3, which is over here. So I'm going from here to here. And so as I go on the interval, I crossed and one of my places where secant is not continuous anymore. So we would say, no, the function is not continuous on the closed interval. Okay, so if you need help with knowing where these functions are discontinuous, you can look at that sheet that I provided you with. But honestly, I don't really have that sheet memorized. I just kind of figure it out because I remember that secant is the reciprocal of cosine, right? And so when I do this, I don't memorize where secant's discontinuous. I just know that secant's the reciprocal of cosine, and that means that I can't have any angle where cosine equals 0. And I know that happens at pi over 2 and 3 pi over 2. That part I do have memorized because that's my unit circle. Okay, so I know that secant can't equal those two values because at those points, cosine would be 0, which is in the denominator when you're talking about secant. So long as our interval doesn't include these discontinuities, then there has to be an extreme value. Now, I don't know if I've got I don't have any more examples for that. But just know, unlike the MBT, remember MBT, for continuity you have to include the endpoints, but for differentiability you don't. With EBT, you have to include the endpoints. So let's just say I gave you a different one now. Let's say I asked you, how about this from 0 to pi over 2? Well, you couldn't be sure. The EBT does not apply anymore because secant doesn't exist at this endpoint, so therefore you can't apply And if you think about it, think of the secant graph that I showed you on that sheet that I printed out. It would look something probably like this at that point at pi over 2. So if we're going from 0 to pi over 2, that's not even possible. You can't reach pi over 2 with vertical asymptote. So this doesn't even make sense. So at that point, a better way to think about it would probably just be to say, okay, well, it's an open interval. But then the EBT still doesn't apply because EBT has to be on a closed interval. So endpoints do matter with EBT. All right, let's go ahead and take a look at examples 7 through 10 now. All right, so let's take a look at examples for 7 through 10. This is pertaining to what the requirements for the IVT are. The IVT is kind of a strange theorem. So basically it says that, if you go from this point to this point, somewhere along the way you had to cross something in the middle. But once again, it has a couple of requirements to it. First of all, it has to be continuous. And it has to be continuous on the closed interval. Second of all, the value that we're trying to get it to equal, it has to actually be between the endpoints. Oops. So the y value that they say it's trying to equal, it has to be between the y values of the endpoints. So, which kind of goes without saying. That's kind of what the theorem says, but it's something you want to check on. And then also the endpoints cannot equal each other. All right. If the endpoints equal each other, then that kind of rules this out anyway, right? So like if you're going from point A to point B and your function never changed, then there's no, the y values are equal at these points, right? It didn't change its height, so therefore there can't be something in between those two y values. They're at the same height. So there you have it. Those are the requirements for the IVT to apply. Is that it has to be continuous in the closed interval, and the value that we're trying to assure exists has to be between the two endpoints, and furthermore, those endpoints cannot be equal in height. So let's go ahead and take a look at this example here. We're looking at the tangent function, and we're going from pi over 6 to 7 pi over 6. So once again, going back to our little worksheet here, where did it go? Okay, so here's tangent. Tangent looks like this, and let's see here. All right, so actually tangent has the same domain restrictions as secant does. So it's at pi over 2 or any 180 degrees or pi radians after that. So same domain restrictions actually. So in other words, tangent is undefined up here and down here. And once again, I really don't take the time to memorize that. I just remember that I do memorize and remember the fact that tangent is sine over cosine. And so as you see, that it makes sense that tangent would have the same domain restrictions as secant, because just like secant, cosine's in the denominator. So let's go ahead and check this one out now. So we have our criteria that we need to check out. Let me try to bring back my criteria that I had listed up there earlier. I don't know if I'll be able to backspace. Nope, I gotta rewrite it. Maybe I'll just rewrite it. All right, so our criteria were that the function has to be continuous on the closed interval. It has to, the value that we're trying to find has to be between those endpoints. And then finally, the endpoints cannot be equal to each other. Those are the requirements for the IVT. So let's see if it applies to this particular example that I have here. All right, and so let's just say, can we use the IVT to prove that tangent of C is equal to 1. There has to be some value of C on that interval where tangent of C is equal to 1. Well, since tangent has a discontinuity here and here, we're going from pi over 6 over here to 7 pi over 6. On that interval, we are crossing a point of discontinuity, and therefore the IVT cannot be used to guarantee that tangent equals anything on that interval. So we would say no, since it's not continuous on the interval. Okay, but let me throw a couple of other scenarios at you guys really quick here instead of just this one before I move on to the next one. Let's look at some other situations. Let's say I were to think here for a second. So let's use a different function here to make another point. Let's say I had x squared is equal to f of x, right? And I wanted to prove that somewhere on the interval from -1 to 1, that f of x equals 0, let's say. So f of c equals 0. Well, for this one, it's continuous everywhere because it's a polynomial, so we're good there. But let's check out something else. Let's plug in our limits here. If I plug in -1, I get 1. If I plug in +1, I still get 1. Those are equal. But our limits can't be equal, our endpoints can't have equal y values. So that rules out the possibility of using the intermediate value theorem as well. Let me try to come up with a third and final example, maybe I'll do 4 examples for you guys, kind of show you different things that happen here. Okay, so here's another example of where the IVT cannot apply, but it's for a different reason. Cosine is continuous everywhere. It's just a wave. It never has any holes, gaps, or jumps, so that's fine. So we're good here. Doesn't matter what the interval is. It's always continuous. Let's go ahead and plug in our endpoints. If I were to do f of 0, I would get 1. And if I did f of pi over 2, I'm going to get 0. Those are not equal, so that's good too. So we've got that one. But take a look here, f of c equals 2. So that kind of represents our k value. So in this case, is 2 in between 0 and 1? And the answer is no. So in this case, we would say no, this function is not continuous because f of c is not in between f of a and f of b. Okay. So just to make a slight little change to this, to make it actually work, is if I change this to 0.5. Okay, now yes, it's continuous. No, the endpoints don't produce equal outcomes. And now for this one, now 0.5 is between 0 and 1. So this is an example of where the IVT exists. There would have to be some value of x that you can plug in to your function, which we'll call c. That would have to give you 0.5. Okay? But in all those other cases, the IVT doesn't work because either it's not continuous, the output's not between the two endpoint outputs, or the two endpoints have equal outputs. Those are all criteria that can ruin your ability to use the IVT. Okay, so you just have to check those 3 things to determine if the IVT. All right, so for examples 11 through 13, we want to find the relative extrema. Okay, so relative extrema, you guys remember, those are places where the function has a peak or a trough, if you will. And that can happen either where the derivative is 0, like on this case, or where the derivative is undefined, like in these cases, because there's no derivatives at cusps. So, to do this, the first thing we need to do is we need to find our critical values. And to find your critical values, you want to find where the derivative equals 0 or where the derivative is undefined. Now, I'm writing this just for teaching purposes, but polynomials never have an undefined derivative, so I'm not going to bother with that one. But over here, we do need to find the derivative. That would be negative 3x squared minus 2x plus 1. And we want to find where does that equal 0. And my guess is that this one's going to factor okay. I'm going to start by taking out a negative 1. You don't have to do that. I just find that negatives confuse me a little bit when I'm trying to factor. So bear with me in my weaknesses. But 3x and x would make 3x squared. And then 1 and 1. I need one of those to be negative. Pretty sure this is a positive and this is a negative. So this one does actually factor. And therefore we end up with two critical values. If I set this equal to 0 and solve, I get 1/3. And if I set this equal to 0 and solve, I get negative 1. So I've got two critical values, two places where this function might have a relative extrema. Now, how I'm going to solve this particular problem is there's two ways you could do it. You could use the first derivative test or the second derivative test. I'm going to start by showing you guys the first derivative test. Most of the time, the first derivative test is easier, and because and the other thing about first derivative test is it always works. So here's how the first derivative test works. You draw a number line, put your critical values on the number line, and what we're going to do is we're going to plug in numbers to the left and right of each of our critical values to see what's going on. So let's pick a number to the left of negative 1, like negative 2. Let's pick a number between negative 1 and 1/3, which would be like 0, and a number to the right of 1/3, like 1. So I'm going to plug these values into my derivative function. I'm going to go ahead and use the factored one, but you can use the original derivative also if you want to. So if I were to plug in a negative 2 here, you're going to get negative 2 take away 1 negative, so that's going to be a negative. Negative here makes a negative. Give 3 negatives makes a negative. So this comes out to be a negative slope on that interval. And if you plug in 0, you're going to end up with a positive slope. And if you plug in 1, my bet is on negative. But let's see. Positive, positive. Yep, it's negative again. So there we have it. So the function is going down, up, and down. Now, you do technically need to make sure that these points actually exist on your function usually by plugging them into the original, because it's possible that there's a hole or a gap or a jump there, in which case you would not say that that is a relative extrema. However, in this case, I know that it connects, and the reason I know that it connects is because this is a polynomial, and polynomials are continuous everywhere. So therefore, at this point, we have a relative extrema that's a minimum, and at this point we have a max. Okay. So it says find all points. Now, since it's asking for a point, they want us to write it as a point. So the x value is negative 1, and the x value is 1/3. The y value would be whatever you get by plugging in negative 1, and whatever you get by plugging in 1/3. So you can use a calculator if you want to on these problems. I'm not going to, but notice to find the y value, by the way, you plug it into the original function, right? And to find the slopes, you plug it into the derivatives. So you got to pay attention what you're plugging it into. Now, another way that we could have done these problems, instead of doing the first derivative test, is we could have done the second derivative test. The way that the second derivative test works is you're going to find your second derivative. So here's my first derivative. The second derivative would be negative 6x minus 2. And what you do in this case is you plug in your critical values into this expression here. So if I plugged in a third, I would get negative 6 times a third is negative 2, take away 2 is negative 4. That means my graph is concave down at this point, which means that if it's concave down and the slope is 0, well, that must mean that this is a relative max. And if you plug in your other critical value, negative 1, to your second derivative, you're going to get 6 take away 2, which is a positive 4. Since it's positive, my graph is concave up, and since the slope is 0 at that point, that would mean that this one's a relative min. So there's two ways you could do it. You can just do the number line test, or you can find the second derivative and plug your critical values into that and look at the concavity instead. However, I want to caution you, it's very rare that this is the better way to go. It works really well with polynomials, but if you're looking at anything else, the second derivative test is kind of a pain in the butt just because finding the second derivative sometimes can be a lot of work. So I would just go with the number line test most of the time. Here's another one. So in this case, I would definitely advise only doing the first derivative test because finding the first derivative is going to be a pain in the butt enough. Finding the second derivative is going to be worse. So let's go ahead and begin our process here. So once again, we want to start by finding our critical values. So to do that, we need to find where is y prime undefined and where is y prime equal to 0. So the first thing we need to do is we need to find our derivative. Now you can do this two ways. One way is you can rewrite it like this and just use the power rule with a chain rule to find the derivative. The other way, which I think most of you guys will be comfortable with, is just doing the low d high rule. So I'll do that one. Low d high minus high d low, draw a line and square below. This is just going to go away because it's being multiplied by 0. And so on the top I have negative 16x, and on the bottom I have x squared plus 4 squared. And now what I want to do is I want to find out where is this thing 0 and where is it undefined. So actually I'm going to rewrite this a little bit differently. I'm going to put my derivative up here, and I'll show you why I'm doing that in just a second. When you're dealing with rational expressions, if you want to find where a rational expression equals 0, you just take the top. Where does the top equal 0? And that's easy. That just happens at x equals 0. If you want to find where a rational expression is undefined, you look at where the bottom equals 0. Now in this case, you're not going to get a solution, and I'll show you why. There is no such thing as the square root of a negative, unless you want to talk imaginary numbers, but we don't do that in this class. So there is nowhere where the derivative is undefined, in other words. So we won't use that. We only have one place where possibly there is a relative extrema, because I only have one critical value. It's x equals 0. So I'm just going to go with the number line test here, 0. I'm going to plug the number to the left and right of 0 into the derivative to see what the slope is doing at that point. So let's plug in negative 1. So if you plug in negative 1 on the top, you end up with positive 16. And the bottom, no matter what you plug in, you're always going to get positive because the bottom is being squared. So I've got a positive over a positive, which means that my slope is positive. Next, I'm going to plug in a positive 1. That's going to end up giving me a negative outcome. So there's that. Now, is my function actually defined at this point? If you plug in 0, will you get an actual answer over here? The answer is yes, you would get 2. Try plugging in 0 for x, you'll see what I mean. So yes, the pieces actually connect. There's no holes, gaps. So we would say that we have a relative max at the point 0, 2. Plug 0 into your original function, you get 2. there's no relative minimum for this function because we only had one critical value and it was a max. So you don't always have to get, sometimes you get neither. Here's another one. Let's do another relative extrema. So for this one here, we want to start by finding the derivative. So let's do that. We have the derivative secant, which is secant tangent. And we don't change the inside. But this is a chain rule, so we do want to multiply by the derivative of the inside, which is 2. So if I multiply this whole expression here by 2, I end up with 4. So there's that. All right. So now we want to find where secant is undefined and also where it is equal. Well, not where secant is undefined, where the derivative is undefined and equal to 0. So let's go ahead and do that. Negative for secant of 2x, tangent of 2x. Where does that equal 0? Well, first of all, just divide both sides by 4 and get the same expression, just no 4 in the front anymore. And now, since these are being multiplied, we can use the product, or not the product rule, the zero product property, which says that one of these then has to equal 0. So we have to ask ourselves, when does secant ever equal 0? Well, remember, secant is 1 over cosine, right? So when does this ever equal 0? Well, if I multiply both sides by cosine, I end up with this, which has no solution. There is nowhere where secant will equal 0. How about tangent, though? Tangent, in case you guys forgot, is there's a couple ways to handle this, but tangent is sine over cosine, right? So for this one, if I multiply both sides by cosine, I get this. Now, where does sine equal 0? Sine equals 0 anytime the angle inside is equal to 0 or pi. 0 or pi. So that means that 2x can equal 0 or 2x can equal pi, and we just solve both of these. So there are two possible values of x here on our interval that can give us some critical values where this function is equal to 0. But are they both really on the interval? Let's take a look here. We're going from pi, which is here, to negative pi. So anything on this interval and this interval. So it's like we're starting down here at negative pi and working our way all the way around here to positive pi. So basically, it's almost like the whole unit circle. And so, yes, we do cross pi over 2. And yes, we do cross 0. So both of those are acceptable outcomes. So these are critical values where we would want to test for some relative extrema. Let's go ahead and continue checking here. So that's where my derivative equals 0. Let's go ahead and find where it's undefined. Where are these things undefined? Okay. So, well, this expression would be undefined anytime either this or this is undefined. So when is secant undefined? Well, remember, secant is undefined when the bottom is undefined. Okay, so in other words, anytime the bottom equals 0. So if cosine equals 0, then secant would be undefined. And by the way, the same thing applies to tangent. For tangent, since it also has cosine 2x in the denominator, it has the same criteria for where it's undefined. Okay, so where does cosine equal 0? Because that's where it's going to be undefined. Cosine equals 0 at pi over 2 and at 3 pi over 2. Okay, so in other words, here and here. Okay, now since we're starting at negative pi and working our way around to positive pi, if I'm at negative pi, I'm not going to call this point negative 3 pi. I'm not going to call this 3 pi over 2. I'm going to call that negative pi over 2. And then we cross positive pi over 2 here. And we've already got pi over 2 here, so that's just double counting it. So we don't really need to count it twice. So I've got 3 possible places where I could have some critical values here. Okay. Now we want to find, and once again, I would encourage you guys doing the number line test here, not the second derivative, because if you try to do the second derivative test, you're going to end up with a product rule, and it's going to look really ugly, so stay away from it. Let's go ahead and do the number line test. So we have negative pi over 2, we have 0, and we have positive pi over 2. And we just want to pick some numbers. Now, since you got to keep in mind, since we're plugging these into tangent function, or sorry, trigonometric functions, you're going to want to be plugging it into, you want to be picking numbers that are actually nice to figure out on the unit circle. All right, so let's pick a number that is to the left of negative pi over 2. Let's go ahead and say like negative, how about negative, I really like anything that's going to give me a normal number here. So if you know your unit circle really well, you can figure it out. I know that cosine equals a half when cosine is at 3 pi over 2. So let's do that, or 2 pi over 3, I mean. And anything between negative pi over 2 and 0. Say that one's good. Negative pi over 3. How about between 0 and pi over 2? Just do the opposite signs here, I think. So in the interest of time, I'm just going to go ahead and plug one of these in, and then I'm going to just say, you can try it if you want to, but I'll just have the answers in advance for the other one. So let's go ahead and plug these into our derivatives and see what we get here. So if I multiply these, I get negative 4 pi over 3. Okay, and once again, you got to kind of know your unit circle to be able to figure out what these things equal. 4 pi over 3 is usually here, but when you're working backwards, it would be like about here, I think. So we're really kind of up here on our unit circle if we're working backwards. Okay, so the secant value at that point, I know that cosine at that point would be a negative half, and so the reciprocal of that is a negative 2. Okay, so we would have my secant value at this point is negative 2. Tangent at this point on the unit circle is negative radical 3. So I've got 3 negatives, so my outcome is negative in this case. Now I'll just go ahead and show you, I'll go ahead and do the rest of these really quick and just put the answers up for you guys so you guys can see. That's how you would have to do it. How much of this can you guys expect to see on your FK? I really don't know. I mean, it is fair game. They definitely could ask you stuff about trig functions. Okay, so here's our outcomes here. We have a negative slope here and here and a positive slope here and here. So notice that the slopes didn't change at these places. So therefore, neither one of these critical values are going to give us relative extrema. Now the 0 is possibly a relative minimum because there the slope is going from negative to positive. Okay, but we have to make sure it actually exists. So let's go ahead and plug this into our original function really quick and see if it actually exists. So what is secant of 0? Well, to answer that, I would first of all ask myself, what's cosine of 0? Cosine of 0 is 1, and then I take the reciprocal of that. So the reciprocal of 1 is 1, and 1 times negative 2 is negative 2. So it does exist. The answer is negative 2. So therefore, we would say that our function has a relative minimum at 0, negative 2. Okay? So that was a really tough question, a lot of trig review there, but oh well, can't hurt to review, right? Let's move on to the next one. Okay guys, so here's our example for numbers 14 through 17. For these problems, it's really just kind of a test of your knowledge about the second derivative test, which is something I alluded to already earlier. So what you're going to be given is you're going to be given a y value, the slope at that point, and the second derivative. So let's just say that I'm given a specific y value of like 2. Right? Doesn't matter where I put it, just as long as it's too high. And let's say I tell you that the slope is 0. That means that there's a horizontal tangent line there. And that means that it's either a relative min or a max. Okay? So if it's like this, that would be a relative min. Or if it's like this, that would be a relative max. And the difference between those two scenarios is whether the graph is concave up or down, which is what the last piece is all about. If I were to give you a positive number here for this, then that would mean it's concave up, which would mean that this value here, C, is where a relative minimum occurs. But if I were to make it a negative number, then that means we have a concave down function, which means that C is now a place where a relative max occurs. Okay, but now I want you to understand the y value is kind of irrelevant. I mean, this is actually what the min or max is, but whether it's a min or max is based completely on these two numbers. This one has to be 0, and then this one, depending on whether it's positive or negative, will determine whether you have a minimum or a maximum. Okay, so that's pretty much the gist of it. Move on to the next few there. All right, these are some examples for 18 through 21. Just kind of reviewing some basic vocabulary stuff with you, and we've already alluded to a lot of this stuff already as well in previous problems, but just clarifying things. First of all, to do exercises 18 to 21, you know what a critical value is. A critical value is where the derivative is 0 or where it does not exist. That's what a critical value does. Now, how does it relate to a relative extrema? If C, actually, let me rephrase that a little bit differently. Oops. If x equals C is a relative extrema, I'll abbreviate that, x equals C is a critical value. So if it's a relative extrema, it's definitely a critical value. But the converse of that statement is not true. In other words, if x equals c is a critical value, it may or may not be a relative extrema. Okay, and the only way to know if it is or not is by doing either the first derivative test or the second derivative test, which we addressed in previous questions already. How do you know when critical values and relative extrema? How do you identify critical values and relative extrema with function equations? So if I give you an equation, then basically what you have to do is you have to find the derivative and set it equal to 0 and also find where it's undefined. How do you identify it with graphs? A little bit different. So what I'll do is I'll do both of these. I'll do an example for both of these. So like for instance, if I said what are the critical values for this expression here, right? So what we would have to do is we would have to find the derivative of this thing. And we would have to set the top equal to 0 to find where the derivative equals 0, and we have to set the bottom equal to 0 to find where it's undefined. And whatever answers we get for that, that would be the critical values. That's how you do it for equations. Now, if you want to take a function, for instance, it kind of depends on what I give you. If I give you a graph of f or if I give you a graph of f prime. So we'll look at both scenarios here. So let's say I have a graph of f that looks something like this. Okay. Well, remember, it's where f prime is either 0 or undefined. So when you're looking at a graph of f, then the place where the derivative equals 0 is at a relative max or a min. So that would be a critical value there, whatever that x value is. And it's also a place where the derivative is undefined, and that would be like at a cusp, for instance. So that's another critical value. That's if you're looking at f. Now, if you're looking at a graph of f prime, I'll draw the same graph here, but it's not f this time. Let's say this time this represents a derivative graph. Well, it's anywhere where the derivative is equal to 0 or undefined. Now, if this is a graph of f prime, then it equals 0 here and here. Those are both critical values. Okay, it's where it touches the x-axis. Whether or not it's a relative min or a max depends on whether it goes from positive to negative or negative to positive at that point, but that's not what the question's asking right now. It's just asking what's a critical value. It's where it touches the x-axis, or if I were to have like a hole in the graph somewhere, like let's say there was a hole here, then that would be another critical value. Anywhere where the derivative doesn't exist, or is undefined, or where the derivative equals 0. Okay, so that's how you can identify critical values. Jump into talking about numbers 22 through 23. For these particular problems, you're going to be given a graph, and your job is going to be to identify the derivative of it. Okay, something we did a little while back. So given the graph of f, which operation best indicates the derivative? Okay, so in other words, the slope function. Well, you may notice that from here to here, the slope is negative. And you'll notice that from here to here, the slope is positive. And then you'll notice that right here, the slope is 0. Second derivative is first derivative. Okay, so if I wanted to sketch this, I would need to sketch a function. If I wanted to sketch the graph of f prime, what I would need to do, I'll say that this is going to be the graph of f prime. I'll do it in green. F prime equals 0 at x equals 2, which means it's going to touch the x-axis at x equals 2. And anything after x equals 2, f prime is positive, represented by the yellow portion of our graph there. So it's going to be above the x-axis there. And anything to the left of 2, f prime is going to be below the x-axis because, as represented by the pink, it's negative. So this green line here would represent the graph of f prime. That's one type of question you'll be given. Let's take a look at another one here. Same directions. So for this one, the slope is positive here, and it's positive here as well. But right about here in the middle, at that point 0, the derivative is 0. So this is an interesting function because the derivative equals 0 at 0, but it's positive everywhere else. So how would we draw that? Well, if I wanted to draw the derivative function, it's positive to the left of 0, it equals 0 at 0, and then after that it's still positive. Suit up with a parabola with its vertex right at the origin there, representing the graph of f prime. Now, the question can be worded a little bit differently, and I'm not sure what it looks like on your guys' lesson, so let me throw some other ideas. Let me look at your guys' worksheet real quick, and I'll get back. Okay, so I was looking, and in one of your questions, you're given the graph of f, but you're asked to find the graph of f double prime. Now, when you're looking at double prime, what that represents is concavity. So we're going to switch gears here a little bit, and we're going to identify something different. So from here to here, my graph is concave down. That means that my second derivative would be less than 0. And the interval from here to here, my second derivative is concave up, so that means greater than 0. Okay, so if I wanted to sketch a graph of f double prime, then it's going to be negative to the left of 0, but positive to the right of 0. So it doesn't really matter how you draw it, just so long as it's positive to the right of 0 and negative to the left of 0 and 0 at 0, then you'd be good to go. And the reason it's 0 at 0 is because at that point you're switching from a negative to a positive, and that also happens to be what we call a point of inflection, because your second derivative is changing signs at that point. Okay. So second derivatives are where you look at concavity. First derivatives are where you're looking at slope. All right. Last set here, limit definitions of derivatives. This is actually something I wanted to put on last week's, but I figured I was giving you too much already at that point, so I didn't put them on there. But let's talk about the limit definition of a derivative. So before I start going through this, let me give you guys some background information here. This is what we call a difference quotient. And what it basically boils down to is that's an average rate of change. It is y2 minus y1. And the bottom here used to be two things being subtracted. It was x plus h minus x, which just simplifies to h. So it's x2 minus x1. Okay, so this is basically just your slope formula written in a little bit of an odd way. And what happens is we're going to take the limit of this as x approaches, I'm sorry, not as x approaches, as h approaches 0. Okay, so the reason we're doing that is because right now, this is like y2 and y1, And those are two different y values because I'm plugging in two different x values. But if I let h go to 0, then these become the same x value and therefore the same y value. So usually a slope is something that tells you the y2 minus y1, x2 minus x1 over 2 points. But if you let those points come together into one point, you end up with an instantaneous rate of change, also known as a derivative. Okay, so I'm going to write it up here again a little bit more clean. So a derivative basically is a limit as h approaches 0 of f of x plus h minus f of x over h. So what this represents, now how do I know that's what these are? Well, just look at it. I mean, it totally looks like an x plus h x over h kind of situation, right? And so this would represent my function. It's a cube root of x is what it is basically. And the x value that we're plugging in there is a 3 that you can see, right? So in this case, you could tell just by this number that we're finding f prime of 3, so the derivative at 3. And we can also identify what our function is. It's a cube root of x. 3 is the x, right? H is going to 0, so it's just the cube root of x is what my function is, right? So if this is my function and I want to find the derivative at 3, then what I'm going to do is I'm just, instead of working this out, which you could, there is a way to do this by hand without cheating, so to speak. But I'm going to use the cheating method, which is basically just doing the power rule. So we have that. F prime of 3, f prime of x then would be 1/3 x to the negative 2/3. Okay? And so that means that f prime of 3, which is what this thing equals, and that's what we're trying to find, is 1/3 times 3 to the negative 2/3 power. Okay? So I'm going to rewrite this a little bit. And there we go. So what did I do here? First of all, I took this piece and I put it in the denominator because that is a negative. Second of all, I squared the 3 to get 9, and the 3 represents a cube root. So that would be the solution to that particular problem. So before I go on to the next problem, I want to show you something. So we ended up having this. Now, by the way, you don't have to watch this part if you don't want to. It won't help you with this week's work. But, you know, it's math, and so it might be beneficial. Technically, since we're doing multiple choice, they probably wouldn't leave the answer like this because the square, or the cube root in this case, is in the bottom. Now, how do we deal with that? Well, it may not be what you think. You guys know that what we're used to doing when we're dealing with roots is multiplying the top and the bottom by the root, right? But the problem is that works with square roots. It does not work with cube roots. Okay, so it's a little bit different. So let me kind of try to transition this a little bit to help you guys understand. Instead of writing that as a cube root of 9, I'm going to write that as 9 to the 1/3. Now, what can I multiply by 9 to the 1/3? So I'm just going to write this separately quick. What would I multiply 9 to the 1/3 by in order to get 9 to the first power? Well, it would be 9 to the 2/3, because when you multiply these, you add those exponents, that becomes 3/3, which is 1. So in this case, what we would have to do is we would have to multiply the top and the bottom by 9 to the 2/3 so that it's no longer a root anymore. Because remember, we don't want a root in the bottom. So when I put these together, it just becomes, top is going to be 9 to the 2/3, because when we multiply those, we just get 9 to the 2/3. On the bottom, then we have 3 times, and we put those together, you get 9. Okay. Now, this also can be simplified. First of all, I'm going to write it like this. Okay. And then I'm going to square that 9 there, and I'm going to get 81. Now, 81 breaks down into 4 3s. Okay. Oops, I don't like how I wrote that 3 on the outside there. It's supposed to be a cube root, not a times. Okay, so now we're looking for the cube root. Cube root means you're looking for groups of 3 things that are the same, and you can pull that 3 out. So now we have the following. 3 cube root 3 times 9. Those 3's cancel out, and now this is as simple as it gets. So, once again, that's not on your guys' worksheet for today, but good math to know, and it's possible that thing could show up on a multiple choice test, but on FRQ, you don't have to worry about it at all. Let's take a look at another one. So, on the last problem, we talked about this. We said that the derivative of a function is equal to the limit, as did it again, h approaches 0 of f of x plus h minus f of x over h, right? But there's another way to write this. The other way of writing this is with something called the alternative form. The alternative form of the limit definition of a derivative looks like this. They're both just different ways to calculate the derivative of a function. The last problem had this format to it. But if you guys look here at this one has more of this format. You can tell because it's not h approaching 0 anymore, right? Instead, they're doing x approaching a number. And the function itself is here, the very first one. So the function we're dealing with is ln of x. Okay, so here's the deal. We have a function, and my function in this case is ln of x. And the value that I'm trying to find the derivative at is this number right here. Okay, so that's what we're trying to find. So this limit definition here is actually a limit definition of a derivative of this function at 5. So instead of calculating the limit in our old school fashion of, doing limits the hard way, we're going to just go ahead and cheat and do the derivative, which is a lot easier. Shortcut that we've learned, right? So if I want to find f prime of 5, the first thing I got to do is find f prime. So since f equals ln of x, then f prime of x, 1 over x. So that means that f prime of 5 would be 1/5. That's it. That would be the answer to that problem. Okay, and that's that. That should do it for our multiple choice review for the week. Hope that was helpful. See you guys later.